Hello there, and welcome to our next video. In this video, we are going to be continuing on with our discussion of rotational dynamics. We're really going to bring everything together here with the idea of angular momentum and rotational kinetic energy. So just like we've seen so far with the rotational dynamics, for every linear thing that we talked about, there's a rotational kind of analog to that. So in linear land, we might think about forces pushing in a straight line. And then when we start rotating, we think about torques that provide a rotational sort of propulsion. And so the same is true for both momentum and energy, which of course are these fundamental concepts that we've learned already. So linear momentum, you recall, linear momentum is mass times velocity. And so impulse is just a change in momentum. So a change in momentum is typically a mass times a change in velocity. And just like we might have linear momentum, like a car driving down the road or a baseball thrown at a batter, we can also have rotational momentum. You can think about a frisbee spinning as it goes through the air, or the wheels on a bike turning. These things have momentum as well. And so the angular momentum, we're going to give the symbol L. And think about the analog. If momentum is mass times velocity, then angular momentum is going to be the angular version of mass times the angular version of velocity. And so the angular version of mass is our moment of inertia, and the angular version of velocity is our angular velocity. So by the same token, we can think about our change in momentum, or our angular impulse, as being I times delta omega. Okay, so we'll look at an example here. So we've got the London Eye was once the world's largest Ferris wheel, big spinning wheel, a diameter of 120 meters, and a mass of 2,100 tons. I mean, it still exists, it's just not the biggest anymore. It completes a rotation every 30 minutes. So estimate the angular momentum of the London Eye while it's in motion, while it's going at full speed. So a couple things to recognize here. A bunch of these terms, I can't really use them as they are. For example, one rotation every 30 minutes, I can't use that because it's not in the right format. But if I want my angular velocity, if I want to think of it as one rotation every 30 minutes, I could convert that by doing still a conversion. So I know that, for example, there's going to be 2 pi radians for every one rotation. And so that's going to take care of my rotation. And of course, I want this in radians per second, so I have to deal with the minutes, which means I'm going to multiply this by 1 minute for every 60 seconds, and then you can see my minutes cancel out. If I do that whole calculation, then my angular velocity will be in radians per second, which is what I need it to be in. And it's not a very big number. It's 0.0349 radians per second. Okay, good stuff. So now I want to know the angular momentum. Well, the angular momentum, as we just learned, the angular momentum is going to be the moment of inertia times the angular velocity. Well, the London Eye is a complicated structure, but I'm going to simplify things and imagine that the London Eye is just a great big ring, and that all the mass is spread around the outside. And so in that case, I'm going to make the assumption that the moment of inertia is just mr squared. That's going to simplify my life a little bit, and it's probably not a terrible approximation. So mr squared times omega, and then I just have to plug in my numbers. Now the mass was given in tons, so 2,100 tons times 10 to the 3 would give me kilograms. And the diameter is not what I need. Instead, I need the radius. And so you can see the radius would be 60 meters. So 60 squared. And then multiply that by my angular velocity, 0.0349. And I end up with a total angular momentum of 2.64 times 10 to the 7, which is quite a bit of angular momentum, but then that makes sense. It's a big, massive structure spinning around. Now let's just stop and think about the units, because we haven't covered that yet. So my moment of inertia is going to be kilograms times meters squared. And then my angular velocity is radians per second. So when I put this all together, this is going to be kilogram meters squared per second. Now that's important to note that the units for angular momentum are kilogram meters squared per second. Note that that's not exactly the same as they are for momentum. For momentum, the units were kilogram meters per second, so they're similar but not the same. And that's because angular momentum is not the same thing as momentum, because it matters how big a circle you're traveling in, right? The same object with a linear momentum traveling in a larger circle would have a different angular momentum, and so that factors into it. So this leads us to impulse. We talked a little bit about impulse already, but recall that linear or translational impulse in a straight line, my change in momentum could also just be thought of as the net force times time. If you want to change the momentum of a car that's driving down the road, you need to apply a net force to it, and you need to apply it over a certain amount of time, and that's going to tell you how much your momentum changes. Well, using that same logic, then the change in the angular momentum, or the angular impulse, is going to be the rotational equivalent of force times the rotational equivalent of time. Well, the rotational equivalent of force is torque. And the rotational equivalent of time is time, because time is time, and it's a scalar, and it's not going to change anything. So this next example, imagine this London Eye. Imagine it's at rest, okay? And first thing in the morning they fire it up, and it takes 30 seconds to get it going full speed. How much torque is going to be required to achieve this? Well, the angular momentum, the change in angular momentum, is going to equal the torque times the time. It's always hard writing tau t, but you'll get the hang of it. So the torque required would be the change in angular momentum divided by the time, which would just be L final minus L initial over time. And the initial angular momentum is 0 because it's at rest. So using my answer from the last question, 2.64 times 10 to the 7 divided by 30 seconds, gives me a torque of about 8.8 times 10 to the 5. And remember, the units for torque are Newton meters, right? So newtons times meters. And again, that's a pretty large amount of torque, but then again, this is a big massive structure, so it's going to require a great big motor to get it spinning and all that stuff. Okay, so the thing about angular momentum is that you can think of it, even though it's not exactly the same as linear momentum, you can think of it as working in many of the same ways, okay? So just like we had conservation of linear momentum, we're also going to have conservation of angular momentum, okay? So an object that's spinning is going to keep on spinning unless you apply an outside force to it, right? And so by doing that, you would be transferring some of the angular momentum to another object, right? So conservation of angular momentum basically just follows from linear momentum. And so if I've got a closed system and all the forces are internal, the total change in angular momentum is going to be 0. Another way of putting that is just that the initial angular momentum is equal to the final angular momentum, right? The amount of momentum in the system stays the same. So a good example of this is figure skaters. If you've ever seen a figure skater, you will note that one of the things they're often doing is spinning around at sometimes just ridiculous speeds, right? And one of the ways they do this is they might start with their arms and legs out wide and begin to spin in a circle. And as they want to speed up, if they want to spin faster, they pull their arms and their legs in very close to their body. And by doing that, they reduce their moment of inertia, right? Because they're still the same mass, that's the same, but if their central axis, if they're spinning around their central axis, by pulling your arms in closer, more of your mass is located closer to your axis of rotation. So they're actually changing their moment of inertia. This is the same thing that's done by divers jumping off diving boards. When they want to rotate very quickly to do flips, they tuck in very closely. Skiers and snowboarders use this exact same trick, that when they want to rotate quickly, they make themselves smaller, and then when they want to slow the rotation, they make themselves larger. They spread out. So imagine we've got a figure skater and their moment of inertia is 6.5 kilogram meters squared, while their arms and maybe their legs are outstretched. And she's spinning initially with an angular velocity of 8.2 radians per second, and so she pulls her arms and legs in, and as a result is going to spin more quickly. Well, if we think about angular momentum, her initial angular momentum has to equal her final. There's nothing coming in and taking momentum away from her, right? Like she's not like throwing a rock or whatever and changing the momentum of her system. So that this is what it is. And so the initial the initial moment of inertia times the initial angular velocity is going to equal the final moment of inertia multiplied by the final angular velocity. And so my final angular velocity is going to equal I omega I over IF. And so we can crunch the numbers here, and her initial moment was 6.5 times 8.2, divide that by 3.8. And when we crunch all the numbers there, it ends up with a total angular velocity of about 14 radians per second. So you can see that she'd be spinning much faster. So one of the things to think about in this case is, how did her energy change in this process? We know that her momentum stays constant. Her angular momentum was the same before and after, but by changing her moment of inertia, she was able to rotate more quickly. Well, it might not surprise you to learn that overall this process, even though her momentum stayed the same, her mechanical energy actually increased. So this faster rotation actually meant she had more kinetic energy. Now, this all ties into the idea of rotational kinetic energy. So it will not surprise you to learn that there is a rotational version of everything, and one of those things is rotational kinetic energy. So when we've been talking about kinetic energy so far, we've been thinking about translational or linear kinetic energy, right? You throw a ball or you run in a straight line, and so you've got a certain amount of kinetic energy, and that kinetic energy you would calculate as being 1/2 mv squared. But of course, that's just something going in a straight line. You can imagine if I had a large wheel, right? And if I spin that wheel and hold it in place, as that wheel spins around and around, it's not really going anywhere. When I ask you what the velocity of this wheel is, that's kind of a tricky question, because it's not displacing. Like, its displacement is 0 overall, so its velocity appears to be 0. And yet very clearly it's spinning around really quickly, right? And if you were to just put your hand on that wheel, you would notice that the wheel could do work on your hand. So very clearly this has energy, and that energy is energy of motion, so it's some form of kinetic energy. Well, what it is it's rotational energy. And so we can talk about the rotational energy not being a function of its velocity, because it's not really getting anywhere, because it's not displacing, but we can think of it as being a function of its angular velocity. And so far, this kinetic energy, you might put a little T there for translational. There is another kind of kinetic energy, I'm going to call this EKR, for rotational. And the formula for this is not going to surprise you. It is 1/2 I times omega squared. Because again, I is like the rotational version or equivalent of mass, and angular velocity is the rotational version of linear velocity. So now, before we move on from this, it's important to just stop and think about the units. Now, the kinetic energy, the translational kinetic energy, the units are very clearly kilogram meters squared per second squared, which of course we never call it that, we just call it a joule. Well, what are the units for rotational kinetic energy? Well, moment of inertia is measured in kilogram meters squared, and angular velocity is radians per second, so that squared would be per second squared. You'll see that those are the exact same thing, so this is also measured in joules. Now this is important because energy is energy is energy. Because energy can only be transformed from one form into another, different types of energy must all have the same unit. And this is why gravitational potential energy and spring potential energy is all measured in joules, and so too must translational kinetic energy, and therefore rotational energy, be measured in the same units. So in this previous example, we came to the conclusion that this figure skater must have increased her mechanical energy. And so how is this possible? Because, well, where did this energy come from? Well, first let's just prove that in fact work must have been done on the figure skater. Like, there's no way around this. There definitely was work done. So let's think about her initial energy. So her initial rotational energy is 1/2 I initial omega initial squared. And so this is 1/2 times 6.5 times 8.2 squared. And this ends up being right around 220 joules of rotational energy. Now her final energy is 1/2 I final times omega final squared. So that's 1/2 times 3.8 and then 14 squared. And this ends up being about 370 joules. So you can see very clearly that since E final is greater than E initial, therefore work was done, right? The work on her can't be zero because she gained mechanical energy. It's important to think about why that is, and let's think about it in two ways. First of all, if the momentum stayed unchanged, and momentum involves moment of inertia and angular velocity, how is it that the kinetic energy, the rotational kinetic energy changes when it involves the same variables? And the key insight there is that, of course, the energy depends on omega squared, right? And so even though we're multiplying these same variables together, a larger angular velocity makes a bigger difference to the rotational energy than it does to the momentum. So that's kind of mathematically why. But let's think about where that work is done, or how that work is done, because it certainly doesn't appear that there's any outside forces acting on her. And in this case, the outside force is herself, right? By physically pulling her arms in, she is doing work by pulling her arms in closer. She would require effort to do that. As she pulls her arms and legs in closer, that's going to increase her rotational velocity and therefore her rotational energy. Okay, let's look at one last example here. So we've got a solid spherical ball rolled down a ramp with a height of 5 meters. What is the velocity at the bottom of the ramp? And you can assume that the ball rolls without slipping. Now, let's just think about this as an example. So when I have different shaped objects rolling down ramps, they might behave in ways that are slightly unexpected. First example I want to compare here is, let's think about what happens when I pit a solid spherical ball versus a frictionless cube. And you can place your bets right now on who's going to win this race, but I kind of feel like we know who it is. When I run this, you can see that pretty clearly frictionless cube wins the day. Well, why is that? Well, the most obvious immediate answer is because frictionless cube is frictionless. And I guess that is kind of why it happens, but not for the reason that you might suspect. This cube slides without friction, meaning the only force propelling it down the ramp is a parallel component of gravity and away it goes. Well, the ball is also being pulled down the ramp, and if we assume that the masses of these two objects are the same, then it's the same amount of force that's trying to pull it down the ramp. But there is friction on this ball. The friction, however, doesn't generate any thermal energy because the ball doesn't slip. What the friction does in this case, though, is it provides a torque. So that friction applied to the bottom of the ball provides a torque which causes the ball to rotate. And so the reason that this ball loses the race against a frictionless cube is because its energy gets transformed in different ways. The ball, as it rolls down the ramp, has both translational and rotational kinetic energy, whereas the cube only has translational energy. So all of its energy is going into the down the ramp kind of energy, whereas the ball is getting some down the ramp kind of energy and some of the spinning around kind of energy. Now, if we run this again, but instead pit these 4 different shapes versus each other, this would be an interesting thing to predict. Which of these shapes is going to win the race? In fact, I would suggest that you should pause the video right now and actually make a guess, first, second, third, and fourth, in order, which of these, how are these each going to place, okay? Now, assuming you've paused the video and you've placed your bets on your 4 shapes, let's see how this pans out. When I run this, you can see that there's a pretty clear distinction between my winners. The solid sphere is first, no question. The solid cylinder is second and not very far behind, followed by the spherical shell, and then the ring is just way, way behind. Now keep in mind what's going on here. Each of these balls or shapes at the top of the ramp are all going to have, let's say, the same potential energy. Let's say they all have the same mass. They all have the same radius, just to simplify things. So they all start with a certain amount of mgh at the top of the ramp. And as they go down the ramp, as they roll and accelerate down the ramp, that mgh is turned into both translational but also rotational kinetic energy. Now, even though the solid sphere wins when you get to the bottom of the ramp, if you were to compare the kinetic energies of all four shapes at the bottom of the ramp, they would all have the same total kinetic energy. It's just that it's distributed in different ways. Because the ring has the highest moment of inertia, it has a greater proportion of its energy as rotational energy. And because the sphere has the lowest moment of inertia, it has a greater proportion of its energy as translational energy and not rotational. And so it's got an overall faster velocity, linear velocity, than the ring. So let's see how that compares to our problem here. So a solid spherical ball rolling down a ramp. Okay, well, let's draw ourselves a little picture. Okay, and so the ball rolls down the ramp, and as it does, let's just draw our forces because it's just good practice. So I've got a force here, force of gravity. I've got a normal force. Now the normal force is going to actually be on the surface pushing upwards. There's my normal force. And then the friction force would actually be right here at this edge pulling up the ramp. Now that's again worth thinking about. Because there's an axis of rotation right in the center of the ball, notice how the force of gravity isn't going to provide any torque because it's acting at the center of the ball. And the normal force, even though it acts here at the edge of the ball, is cutting through the center of mass, and so it's not going to provide any torque either. It's only the friction force. The friction force is at the edge of the ball. It's located a certain radius, a certain distance away from the axis of rotation, and it's acting perpendicular. It's acting tangential to the surface itself, so it's going to provide that torque. Okay, so how do we find the speed at the bottom of the ramp? Well, this is going to come down to energy. The initial energy has to equal the final energy. So at the top of the ramp, what do we have? Well, at the top of the ramp, we have potential energy. And at the bottom of the ramp, we're going to have translational energy plus we're going to have rotational energy. Now let's see how these pan out. The potential energy at the top is mgh. And then the translational energy at the bottom is 1/2 mv squared. The rotational energy is 1/2 I omega squared. Now, a couple things to notice here. First of all, I don't know the radius of the ball, and I also don't know the mass, and so I'm really hoping those things cancel out. And we'll see here in a second, we're going to be in luck. The only thing I know actually is the initial height of the ramp, right? So let's think of a couple things. First of all, the moment of inertia for a sphere is 2/5 mr squared. So I can take this and I can substitute it in right there. And then the second thing, of course, is to remember that the angular velocity is equal to the linear velocity divided by the radius. And so I can take this and I can substitute that in over there. And what I end up with is I've got mgh equals 1/2 mv squared plus 1/2 2/5 mr squared times v over r all squared. Now that's a lot. But if we just zoom out for a second and have a little think about this, what we'll see is two things. One, there's a common term of mass. So the masses, in fact, do cancel out. And that shouldn't be a huge surprise, that mass actually doesn't determine the speed at the bottom. But what's interesting as well here is that this r squared value and then this r, which is also going to be squared, these also cancel out. And so the radius of the ball also has no effect on the speed at the bottom, right? Whether it's large or small. What does have an effect is the shape. All that matters is that it was a solid sphere. It doesn't actually matter the size. And so I end up with GH equals 1/2 v squared plus 1/2 times 2/5 is 1/5 v squared. Now, if I remember how my fractions work, and 1/2 is the same as 5/10, I end up with GH is equal to 7/10 v squared, which when I solve that for v, I get v is equal to the square root of 10/7 GH. And plugging in my values, I get 10/7 times 9.8 times the height of the ramp, which was 5 meters, And solving that, I end up with a speed of about 8.4 meters per second. Okay, awesome. Now, that is it for rotational momentum and energy.